So in this video, we want to talk about how to reduce geometry or how to change the topology of a shape. So why would you need that? There are actually two reasons. Sometimes you really just need some kind of, low-res version of a complex geometry. For example, when you're working with game engines, you might need level of detail versions of your geometry. But even as an effect study, you often need to simplify geometry so that you can use it in your simulations only to an extent that you actually care about. So for example, for collision geometry or for simulation geometry, it doesn't need to be the exact same resolution that you use later for rendering. We will look at this concept in another video. So the first one, first of all, before we start, I brought in here the statue of Mars, and whenever we bring something in, we should always first check the scale. And I usually do this with a Tommy. So let's bring in a Tommy. There he is. Let's move him to the side a little bit, and you can see that's a pretty big statue. So let's scale this down to an appropriate scale so that we don't run into problems later. That's too small, maybe something like that. Thanks, Tommy. And then we will have the problem. Let's right away start with the first node and we will see the problem, and that is fuse, which is a very simple node. And if I use fuse and change the number here, then nothing happens. And the reason is, very careful, this is an alembic. So what comes out of this is a packed geometry. So as usual, we need a convert node. And now we actually have geometry. As we can see, we have proper points and primitives. And now we can see what the fuse node is actually doing. It is actually, like the name suggests, fusing points that are close to each other. And the distance can be controlled here with snap distance. And then it looks like this. If I increase the distance, points start to snap together, and then I can create this version of the same statue relatively quickly. Of course, this is a pretty high-res statue, so it might take a little bit, but here you can see what you can do. Now, a small note on this, the fuse node we only looked at here in the context of reducing or remeshing geometry, but it also is a very helpful tool for solving certain connection problems. So let's say you draw a curve with the draw curve tool and you try to bring it together. You will always fail probably to perfectly align it, even if it's still made of 2 points next to each other. And of course, as you might guess at this point, you can use a fuse tool here to, at some point, just merge those points, boom, there they are, together by snapping them together based on the snap distance. So a very helpful tool, especially when working with curves. And of course, the same is true for geometry. If you wanted to, merge these two geometries here, you can use a fuse, of course, as well. And, depending on the distance, at some point, bloop, they just snap together and it becomes one grid. Very handy. So not only helpful for reducing or remeshing geometry, it's also for closing gaps, basically, for geometry and for curves. Before I move on, because this is a pretty simple node, I want to show you something that will also work with all the other nodes. It's just that here it's a bit easier to do. And that is that all nodes have a group. So keep in mind that you can actually use this to as a visual effect even. You could, for example, take a group and then use a second geometry, like a sphere, for example, as an input geometry, and take this as your bounding box. And you can do this by changing the bounding type to bounding object. And this only works with points. So we have to switch that. And now I can use this to decide basically an area where I want this effect to happen. And if I use this group in the fuse function up here, you can see then that the simplification only happens there. You can already see where this is going. This is a really cool effect because you can animate that sphere. And then you basically can create this low-res version of a geometry on the fly. Let me quickly do this with a smaller version of the geometry so that it's a bit faster. And now the effect is even easier to see when the whole thing just happens in real time. And if I go a bit more extreme, maybe it's even more fun. And here's the idea. So if you want some kind of digitalization effect or something, you can choose the area where this effect is supposed to happen, which is pretty cool. I really like that. Okay, so this is fuse, easy to understand. Let's have a look at other options. When you're coming from another 3D program, Maya, for example, you might be used to a percentage amount that you want to reduce the geometry detail. And for this, there's actually a poly reduce. This works very similar because here you can say, you know what, I want half of the amounts of points that I have currently. So we can just type in here % to keep 50, for example, and then it will rebuild to only half of the geometry. Maybe let's do 5% and it will rebuild that as well. So this is a very nice way, and the difference to fuse is that it tries to keep the shape intact as much as possible, and as you can see, it does a pretty good job here. So if I go down to 2 or even 1%, then you can see we went from 300,000 points now to only 3,000 points, and it still keeps the shape intact quite well. Instead of percentage, you can also change the percentage of the point count, and the same is true for the overall output count. So you can say, instead of percentage, I want polygon or point a certain amount of it. So for example, 1,000 polygons, which means faces in this context, I want to have, or 10,000, for example, and then I get exactly more or less that number, which is here under primitives, roughly 10,000 faces. But sometimes you don't want to just reduce the geometry. Sometimes you want to completely rebuild it. And what I mean by that is, for example, if you have a very low-res version, you might actually even want to up-res. So here you have, and actually I forgot to convert that statue. Let's turn off the visualization of the texture. And you might need a more detailed resolution for this. And of course, you can always use a subdivide, but this will sometimes create strange geometry or soften your geometry too much. So what can be a better solution is a remesh sometimes, because a remesh, as the name suggests, is completely rebuilding the topology from scratch. And this is very similar to the poly reduce, only that you can go in both directions. So you can also increase the amount of detail. What is interesting though, when we have something created ourselves, if you have a sphere and then you use the mountain node to turn it into a rock, as we've seen in the mountain node video, you have one problem, and that is that the geometry ends up pretty high with all the detail that you might want to get out of it. So currently we have 100,000 points, and this is where the remesh can be interesting as well, because not just because you can change the resolution, because that's not interesting, because then you end up again with a lot of geometry and you lose somewhat detail, but it has one interesting option, and that is adaptive. And that means it cannot just rebuild it completely, but will change the resolution based on the detail it finds. And this is interesting. And the parameter that you need here is gradation. And when you increase that, it becomes basically more aggressive with the flat areas. So as you can see here now, it rebuilds the topology based on where it needs detail to rebuild the overall shape as close as possible. And while it's not 100% perfect, you can see that we keep the shape intact quite well. And we went down from 100,000 to only 12,000 points. And that was really just by quickly trying the settings out. So remesh is interesting and different to the poly reduce, because to my knowledge, the poly reduce doesn't have an adaptive adjustment. It's still a very good node, but sometimes you need something where you have, a lot of contrast between high detail and low detail, like here. You need something more adaptable. Now with Houdini 20, actually there's now a new tool that we can use to rebuild the geometry, and that is the quad remesher. So you can actually recreate geometry with a quad-based topology. As you noticed, all the tools we've seen so far work with triangles, and that is actually not a problem. We will talk about this in a second. But if you need quads for some reason, finally now there is a way of doing this. So for example, I brought in here the sculpture of Athena, and as you can see, I matched it with a scale to my Tommy. I think that scale is okay. And then let me drop a quad mesher. It's called a quad remesh, and you can see it's still in beta in Houdini 20.0. And now you can see we turn this geometry, which is based on triangles, because I remeshed it before from a scanned geometry. And with a quad remesh, it now looks like this, at least when you just drop it in. Now, a couple of problems here. We have currently a target quad count of 10,000. There is no percentage function as far as I know. You have to give in the exact number of points that you want, more or less exact. So let's say we want 60,000 because currently we have 220,000. That's a reasonable number. And then you get this, and you can see it rebuilds the geometry with quads in mind, which is pretty impressive. Now, as you can see, it loses a bit of detail, and that's because by default it subdivides the whole thing. If you turn this off, you get a good bit of detail back, as you can see. So it depends a bit on your case. You have to play around what works for you, but you can see it's really impressive what side effects did here. This is on a technical level not easy. If you want to subdivide, you can still then do a project points, which is basically a ray node that projects onto the original geometry. I would say just try out what works best, either the projected subdivision or you leave it as it was before without any subdivision. In our case, I think with the projected points on the subdivision, it's better. You can actually also change the result with the decimation level. Now, this basically means the input geometry that it takes, how many of these points will it use for the internal algorithm. So the lower the number, the faster the result will be, but theoretically at least, the less accurate it is. But that's not always true, because the higher you put it, the more kind of, I would say, high detail noise, that's the best way of thinking about it, you add to the whole thing. So the result will not necessarily be better, but it will be slower. So it's a bit of a, technical problem. Side effects decided that 2 is a very good, average. I would say just play around with a number and see what happens. It's not that higher number gives you better results, but I think it's worth at least trying different decimation levels. If you want to understand better what it's doing, just read the help of the parameter. So a small note on this, because I think a lot of beginner will now tend to remember, oh, the quad remesh is the best tool because it creates quads, because a lot of you have probably learned that a geometry should be made of quads. Let's really quickly talk about this, because this is true only in certain contexts, and those two contexts are A, when you have geometry that you want to model by hand, then quads are much easier, which is not the case here. Or when you want to use the geometry and you want to skin it onto a rig, then quads are also better because the deformations are better. Both cases are not what we usually do in effects though. So be careful with the assumption that quads equal better results. That's actually not true. In Houdini, using triangles is completely normal. Actually, I prefer triangles over quads because the topology is more even when you use triangles. And here's an example of this. If you would use a remesh to rebuild this geometry, in my opinion, you get better results with lower point count. So here we have 50,000 points, and in our example before, this one with quads is a bit more, almost 60,000 points. And in my opinion, you lose detail. That's why the quad remesher, while it's great that it's here, please do not assume this is now the automatic thing that you should use. In the context of effects, quad rebuilding is actually rarely necessary. So make sure that you know why you want to use the quad remesher. Don't use it just because you think quads are better. But anyway, very cool that we have this now with Houdini 20. Just, be aware when and when not to use it. And then another example of rebuilding stuff is when you have more than one object. And what I mean by that is, for example, the statues that we saw so far were always one thing, one closed geometry. But sometimes, and the Tommy is actually a good example for this, you have geometry that is built of multiple elements. For example, Tommy, if you look closely, actually has eyeballs, that he also has some kind of mouth area in here. And he has a shirt and trousers. So he is actually built of different elements. And this can be problematic for simulations, for example. If you want to look at Tommy as one closed geometry, this is something you can do with in Houdini 19, it's a new node called Remesh to Grid. And this looks like this. So first of all, it looks a little bit weird. And what you have to change here is the division size. And it's called division size. And let's first show you what the idea here is. There you have it. We are rebuilding the overall shape with everything included, so to say, including the eyeballs, even though you can't see them well. Let's actually go a bit lower and then you should be able to see them. There you go. So here are now the eyeballs are integrated into the overall shape, even though it's one, closed thing. And you can see even the shirt and the trousers are now part of the whole geometry. And the interesting thing is you can add whatever you want to this. So you can, for example, take a sphere up here, I have no idea why, and when you merge this together, they both will become one geometry basically, and this looks then like this. As you can see here, it is connected. That looks a bit weird, but as you can see, this is possible. This is what you can do with a remesh grid. There's one problem with that though. If you have a resolution that is too fine, then stuff like this can happen where the shirt of Tommy is breaking apart. And the reason is that the shirt was very, very thin. And this is a problem because you have to understand what this node is doing internally, because this technique exists for quite a while. This is a new node in Houdini 19, but the technique is the following. You can, and we will talk about this later, you can turn any kind of geometry into a volume. We can do this with a VDB from polygons node. Again, we will talk about this later. And this is exactly where you find the voxel size again. It's what it was called division size in the remesh grid. And basically what you see here, even though it doesn't look like it, it's actually a volume. And then you can convert this volume back into a geometry with a VDB, convert VDB, convert to polygons. And here you can see this is exactly what we saw before with a remesh grid. My point here really is this technique existed before. It's now built in one node though. Behind that there is a volume conversion happening. And this is why the technique actually works, but it's also the reason why sometimes stuff like this can happen. Where super thin objects cannot properly be converted to volumes, and then you might have to end up with a lower resolution of that volume. Okay, and then finally, there is one last thing we can do, and for this I have this ship example here, because here we have a problem. If we use any of the tools we saw so far, we will actually break this model. For example, let's try a polyreduce here. And first of all, it's very slow, and that is because it has a huge amount of geometry, and also it's, has very fine detail. So this creates all kinds of calculation problems, and also it will actually not work. Let's try something much faster like the fuse, which also will not work. But let's say we wanted to get rid of the fine detail here. Let me quickly change the background so that we can see that better. So if we want to change those ropes here, let's get rid of them, for example, we could try the fuse, but then you will see what happens is that we're not really getting rid of them. We're more like, kind of melting them together. So it doesn't really work, especially since we have points that are really close to each other, and then we have points that are really far from each other and all that stuff. So we are kind of lost here, and this needs a completely different technique, and that needs the measure node. So what we can do with the measure node, like the name suggests, is we can measure different things. And one thing that would be interesting here to figure out is not, changing the topology of something, but figure out how big are different elements of my geometry, to find the small ones or the thin ones, for example. So what we could measure here is what already is the default, the area. And this creates currently an attribute on the primitives. So let's have a look, and we have all kinds of attributes here. So let's filter for area, and there we have it. Area is actually something that is now created, and we can use a blast node to find, let's say, pieces that are under a certain area. And when we do this, we can type here area smaller than, 0.005, then those will be deleted. And that is interesting. Let's do this. But now this happens. Let's go a bit more aggressive to see it even better. So unfortunately, it doesn't seem to delete objects, but it deletes faces. And this is exactly something you have to understand. The measure node currently measures the area of each face, which is not what we want. We want the area of the whole object, for example, the rope or the sail. And this is why we have to change this from per element to per piece. Now, Houdini needs to know somehow what one piece is, and we've already seen here it asks for a class attribute, and we know how to get this. We can use a connectivity node for that, so that it can find the different pieces. And if we look at the area attribute again, and if we turn on and off connectivity, it doesn't change anything. Let's see if the blast does anything different. No, that's not helping. So what's wrong here? Be careful, since this measure node is working on the primitives, it also expects this attribute on the primitives. The connectivity by default, though, creates the attribute on the points. So let's switch this to primitive, and now something has changed. So let's check what comes out of it. And now the area is much bigger, which is a good sign. So let's turn off the connectivity for a second, and the area is much smaller now. And if I turn on the connectivity again, it jumps up to a much higher number, which is indicating that it actually found the whole object and is not analyzing every single face anymore. So now we can work with different numbers. So let's do smaller than 1, smaller than 2, smaller than 3. And now, as you can see, we can delete objects based on the area that they cover. And this means at some point we can actually separate the big pieces from the small pieces, and of course the other way around works as well. So now we have only everything that is smaller than 6 meters in the area, and this is a great way of separating very complex geometries into parts or delete parts. And this would be, take ages to do this by hand, and this is built in with the measure node. So really powerful, and this is why we will look at the measure node in the next video a bit more, because it can do a bit more than just measuring the area. So as we've seen, a lot of ways of reducing or changing geometry. We've seen the very simple fuse node, then we've seen the polyreduce, which can work on the percentage reduction or an absolute output number. Then the remesh node, which can be useful to even increase the resolution, and also which has the internal function of an adaptive resolution change. So if we have something like this, like our rock here, we can kind of change the resolution based on where it's necessary. And then there is the cool option of turning complex geometry that is made of different elements into one. We kind of meld them together, which is especially important for preparing geometry for simulations. And then finally, sometimes you want to simplify objects not by their overall resolution, but by the different scales of objects they have. And there is a way of measuring the area, and we can then delete them based on that. So as you can see, pretty powerful tools, and not all of them, but most of them we will use throughout the course. So I hope this is helpful. Thanks very much and see you later. Cheers.